Hello everyone. So after ASCII, we are going to learn today logic gates. So in the previous classes, we learned what the bits are, what binary systems are, how we use texts, emojis, commands, and how these are stored in the binary form in the devices. Now we have to learn that how we can compute with those bits, and for those computing we need logic gates for it. We will see a few examples of logic gates. So first we'll take single bit gates. What are actually single bit gates? That takes one input and returns one output. But before that, let us first learn about only this. Okay, let's cut this. We will just learn about first this. So what logic gates are? This is a gate. We have used a generic box. It is input, output, and this is gate. See, it takes input through the wire, passes through the gate, it here processing occurs, and here returns output. So now learn about single bit gates. So single bit gates are those that takes only one bit and returns also one bit. Here in single bit gate, it is input. Here we will represent a triangle with it. For gate, it is a triangle, and then output. It takes only one input and returns only one output. And as it takes binary, so it will be either 0 or 1, and output will be either 0 or 1. Single bit gate I have drawn here is called buffer gate. It is called as a buffer gate, where the number it takes and returns also the same number. Suppose it takes 0, it will return 0. Suppose it takes 1, it will return 1. Okay, we can write this as like that. A here we are representing this with A. Output is also A. Just notice here that output is not changing. So this is so I can tell that this gate is doing nothing to that input. So I can simply represent it like this. And one more thing to remember is that it should be read from left to right. It should be read from left to right. So as it is not, as this gate is not doing anything to the input, so we will just give this to a line. And this buffer gate is also known as identity gate. This is also called as identity gate. Let's take a look at the another type of single gate. Another type of single gate is called NOT gate. The NOT gate is just opposite of that identity or buffer gate. It flips the input. It just only flips the input, and we are drawing this like that. We will take a single triangle and make here a small circle. Okay, suppose we give A as input, then we will get A of bar. Here bar is used for negotiation. What happens that it flips the input just because of this circle. This circle helps in flipping this input. Suppose we will give 0 as input, then we will give output 1. If I give 1 as input, then I will get output as 0, just like that. And for these types of gates, we will make a table known as truth table. So for this I will just make a truth, I forget that. I will make a truth table or truth table. Yeah, it is called truth table. So in truth table what we'll do, here we'll take input and here is output, which we commonly represent as a. If I give input as 0, I will get 0. If I give 1, I will get 1. This is a truth table for identity gate. And for here is a truth table. See this, here is the truth table. As I am representing input as a and output as 8 bar is used for negotiation. When I am giving input 0, I am getting output 1. When I am giving input 1, I am getting 0. And I told you that this is just opposite of identity gate. So I can also call this inverter gate, as it inverts the bit. And so next one is always 0 gate. Always 0 gate what performs, when whatever I give as input, it will always return 0 as output. Suppose I give, there is no specific gate here, so I am going to write truth table of this. Here is input, here is output. If I give 0, it will obviously return 0. If I give 1, then it will give 0. So this was always 0 gate. Next one is always 1 gate. It is similar to always 0 gate. It will return only 1 as output. So for input, so if we take here 0, it will return 1, as it is always 1 gate. If I take here 1 here, then it will be also give 0, 1. So these are the four possible single bit gates, single bit logic gates. So next one are 2 bit. Next are 2 bit gates. So how 2 bit function? Suppose it is the gate. It is gate. Here it takes 2 input and gives a 1 output. It gives 2 input. It takes 2 input and gives, here is a gate, and gives output. Suppose it is A, it is B. It will give output C. So here truth table has 4 rows, as it has A, B has 2 inputs and output 1. And so there are 4 possibles, 4 rows, 1 0 0 0 1 1 0 1 1. So it becomes 4 rows. As it has 4 rows and 2 inputs, so there are 16 possible 2 bit gates, but we will only discuss only the 5 most important from Thomas G. Wong's book. Okay, let's do. The first one is the AND gate. AND gate gives output 1 when both the inputs are 1. Means it will only give 1 when both inputs are 1. So its gate is like this. A little bit hemispherical shape, hemisphere shape, and here straight line. So it takes 2 input, gives the output. So what I tell, it will return output 1 when both the inputs are 1. So let's make its truth table. Here input, output. If I take 0 0, then what will be the output? It will be 0, obviously. 0 1, it will be 0. 1 0, it will be 0. And when 1 1, then it will give 1. And like this, if I take input A and B, then the output is AB. And you can also think that 0 multiplied by 0 is equals to 0, means 0 multiplied by 0 equals to 0, 0 multiplied by 1 equals to 0, and like this, and 1 multiplied by 1 is 1. You can think like this. Okay, it was easy. Let's talk about the OR gate. So its gate is like this. This one. Yeah, this one. It is OR gate. No, I have done, I think, wrong. Let me check. So it's correct. Actually, it's correct. Here A, here B. They are both their inputs, and the output will be A plus B. It is not that A plus B. It is not that the arithmetic operator is not functioning like this. So its truth table is just this one's opposite. I am showing you truth table of OR gate. Here is input, output, so if I take input 0 and 0, it will return 1. If I take 0 1, it will give 1. If I take 1 0, it will give 1. If I take 1 1, it will give 1. Okay, 4 1. Oh, no, sorry, it will be 0 only. Okay, not exactly like this, but here 3 zeros, here 3 ones, 1 0, here only 1 1. So when 0 0 input, then the output is 0, and if either of them is 1 or both are 1, then the output is 1. But you can don't think like this, as 0 plus 0 equals to 0, so 1 plus 1 equals to 2. Not that 1 plus 1 is actually is equals to 1. Okay, so you can write the AND gate as output as A, I think this one, no, sorry, this sign B, and here A, this sign B, not A V B. It is actually a sign here like this. Okay, so the next one is the exclusive OR gate. It will be capital letter, sorry, and it will be also capital letter A and D. The exclusive OR gate, or we can also write XOR. Okay, how it functions: when both when either of the inputs are 1, then it will return 1. If both inputs are 0, it will return 0. If the both inputs are 1, it will return 0. So let us draw its gate. It is like this only, with just simple differences there. Here I have drawn this. First I will draw the OR gate like this. Then I will draw a curved line here, and that's it. Here input, and here how output is like that, A plus and a circle around A. Here it is B, A mod B, also called addition of module 2 B. So let's draw its truth table. So here is my truth table. Here A, B, B. If I take both 0, then what I told, it will return 0. If I take either of them 1, it will return 1. Similarly this, when both inputs are 1, it will return 0. Just like that, it was also easy. Next gate, so we'll do 5 gates and 2 are left. So the fourth one is the NAND gate, NAND gate. So NAND stands for not and. Okay, means it is doing the not of and, means the opposite of and. It is doing the opposite of and. So I told you that a small circle is used here that to flip the output. So it is like that. So let's see this. It is AND gate and I will draw a small circle here. See. I've drawn this. Here is a small circle that flips it, and it is actually performing as a NOT. So here input and see here it's AB, and we will as output we'll do AB bar, and you know that bar stands for negotiation, I have told you. So okay, let's draw its truth table. Here I will draw AB bar. If I take both 0, as I told you, it will function opposite of AND. So in AND gate 0 0 both input function output as 0. I will write here 1. Then second one will be the this was in the AND gate was 0, it will be 1 here, it will also be 1, but when both are 1 it will be 0. So remember that this small circle in it is function. When the inputs are going and this function, this flips the output and we get the opposite output. So a last gate is remaining. Let's do that. So the NOR gate. And it stands for NOT and OR. Means it is also similar that it functions opposite of OR. It functions opposite of OR. So how this gate is, it is also same that the small circle is there. Let us draw this. Oh sorry, here is one circle here. Sorry, I am cutting this. I'm drawing this clear. So this one is here a small circle here. Oh, it takes input A, okay. Here bar stands for negotiation. Let's draw its truth table. A, B. Okay, if I 0 0 0 1 1 0 in 1 1. So I told you when either of them in the OR is 1 or both of them is the 1, then it will return 1. So it will be just opposite. So when 0 0 function, it will return 1. 0 and 1 0, 1 and 0 0, 1 and 1 0. In the OR gate it was all 1 and it was 0, and in the NOR gate NOR it is 1 and all the others are 0. Okay, so let us solve some questions of Thomas G. Wong's book. So here is a question. Here is a question. This I have took. Here is two small circles, A here, B here. Then the output is, what will be A, yeah, this one. So you have to write the truth table of this. Pause this video and do this. Okay, so let's do this. A, B. So I told you that small circle is functioning as it flips. So if I take 0 0, then it is flipping its value, means 0 0 turn into 1 and 1, and so for 1 and 1 in the OR gate it will give 1. Clear? Just think this thing, just take it very easily. When 0 and 0 is going there, here is 0 going, here is 0 going, okay, here circle is present, and here 1 is there in the gate, and 1 is coming here, and it will give, obviously give 1. When 1 is coming here, it will obviously means, and from here it is functioning as a OR gate, means here it is functioning as a OR gate, it will return 1. A 1 going, it will return and I told you that in OR gate, if either of them or both are 1, then it will give out 1. So here when I give 0 0 as an input, it will flip it in this, and 1 and 1 will form, and it will give 1. So let us do this, 0 and 1. So this will be a similar case. 0 will be 1, 1 will be 0, it will give 1. 1 and 0, 1 will be 0, 0 will be 1, will give 1. When both of them are 1, see, both of them are flipping its digit. 1 will be 0, here also 1 will be 0, and what 0 and 0 gives? 0 and 0 gives 0. So it was the truth table of this. Let us move to another question. It is also similar. So in this question you have to tell this output. You have to tell this output. Here input is A, and here input is A and B, and here is circle. Here is circle to flip the position. You have to tell that, tell the output.